Hello everyone, welcome back to Codynamics. In this video, we are simulating a 2D cylinder undergoing vertical oscillation using mesh morphing in OpenFOAM. So instead of using a rigid mesh or remeshing every time step, we will use OpenFOAM's dynamic mesh capabilities to smoothly deform the mesh around the moving cylinder. So this is what we call as the mesh morphing. So in general, mesh morphing is all about dynamically adjusting the shape of the mesh without regenerating it from scratch again. This becomes especially useful when simulating problems involving moving boundaries like a deforming wing, a piston inside a cylinder, or even fluid structure interactions in some case. So in today's video, we are diving into this powerful technique in CFD called the mesh morphing. So instead of discarding the mesh and remeshing the domain every time the geometry moves, mesh morphing lets us smoothly update the mesh to follow the motion. To do that, we have certain libraries such as the dynamic mesh dict, which is a general configuration file. Within that, we have a library called dynamic motion solver FVMesh. And under that, we again have something called the displacement Laplacian motion solver. So this setup lets the mesh follow the motion of the cylinder by solving a Laplace equation for mesh displacement with inverse distance diffusion. So meaning cells closer to the cylinder deform more and those far away deform less. So this will effectively keep the skewness in control, and the mesh in general will be consistent instead of just having a very bad mesh even after displacement. So this is perfect for simulation involving vibrating bodies, vortex induced vibration, or if you want to do fluid structure interaction in 2D, you can use this case. But even if you want to do some oscillating cylinders, you can just change in a few parameters and you will be able to do oscillating cylinder instead of vibrating cylinder. So let's get to the video now. All the cases which have been used, like the list of folders that you are seeing on the screen, will be available to you for download in the GitHub. So I'll give the GitHub link in the description, so you can go there, clone the repository, download the cases, and you can use it as you wish. And this mesh is basically from ANSYS workbench meshing. I have given you the mesh, but if you want to use a different geometry, then you can either use block mesh or snappy hex mesh, or if you are comfortable with any other meshing tool like Gmesh, Salome, or Ansys, you can use that and import it here. In this case, I'm not going to go much into the case setup of a transient simulation. This will be more focused on the dynamic mesh dict setup. So if you want to know how to do flow over a cylinder or a prism, then I have already made videos both in 2D as well as 3D, laminar, turbulent, everything. So you can check my previous videos available in the playlist OpenFOAM, and you will be having good enough tutorials to follow this one. Without further ado, let's start with understanding the case setup. So just like always, we have 0.original constant system. If you go inside 0, you will generally have this velocity, pressure, nu-t, and based on the turbulence model which we use, we will have the other case files. Like if you are using k epsilon, you will have k epsilon and nu-t. If it's k omega SST, then you will have nu-t, k and omega. But in this tutorial, we are going to use something called this palette almaras. So we have this nu tilde. So we don't need k epsilon omega, nothing. We just need nu-t and nu tilde, and this will just work fine. But apart from these files which we usually see, we also have a file called point displacement. So this is the major focus for this video. So we will open all of these and see what is there. So starting with velocity, you can see the inlet is in x direction. It's going in 10 meters per second. And then there is an outlet. So this case is basically flow over a cylinder in 2D. So we have inlet, outlet, cylinder, upper and lower, and front and back, just like any 2D case. And for outlet, it's zero gradient. Cylinder, it's no slip because it's a wall. Upper and lower, we have kept it as slip so that we don't have to treat it as no slip walls. And front and back planes are empty. And looking at the pressure, since we already defined what is the velocity for inlet, we have to give zero gradient, and outlet is going to be fixed value uniform zero. As you can see, this is not regular pressure, not in pascals, it's reduced pressure, which means pressure divided by the density. So that's what we are able to see here. And cylinder is zero gradient because we already defined zero velocity on the cylinder. So we have to give zero gradient. Same goes for upper and lower, and obviously front and back will be empty in all the case files, boundary files I mean. And coming to nu-t, we always have the inlet and outlet as calculated uniform zero. and wall is going to be new tk wall function. Upper and lower is also like walls, so we are keeping new tk wall function, and new tilde we are going to keep fixed value uniform 0 at inlet and 0 gradient everywhere else. So these are like the general case setup, so we are not going in depth into what it means and all. So the main focus is this file, the point displacement. So here if you see, we don't have to define for inlet outlet explicitly. So whenever you put dot star, it means everything else. So we have defined for front and back planes, and then we also have defined for cylinder. So whatever is not defined will go for this one. So in our case, that's upper, lower, inlet and outlet. So all these will be taking fixed value uniform 000, and this file is called the point displacement because this is what is going to enable us to modify the mesh or basically move the patch. So in this case we are going to move our cylinder patch. So we are saying the type is solid body motion displacement, that's the type of motion, and this displacement motion needs a function. So what is the solid body motion function? Because displacement can be anything, it could be oscillating, it could be translating, it could be rotating, right? So we are choosing oscillating linear motion. If you want to know what are the other options, you can go to the documentation of OpenFOAM. So this is the place where you can find the functions for solid body motion functions. So I will give the link in the description, you can check. We have a lot of functions here. So we are just going to choose one which is suitable for us, but there are also other functions from which you can choose whatever you need for your simulation and you can perform. So we are just going for oscillating linear motion. If I go in here, we can see all the documentation for that, and if you go to the .h file, you will be able to see what are the inputs which are needed. So basically we need amplitude and also omega, but amplitude is in vector, which means we have to give x, y and z, and omega is going to be a scalar. This is like radial velocity and this is amplitude. And then we also have to give on what patch do you want to make this oscillation. So that's what we are also going to do here. We have selected cylinder. Under the cylinder we are going to give amplitude, which is a vector. So we are saying in y direction it has to move 0.02 meters, okay, and omega is 31.5, which is in radians per second. So I hope this is clear. If you change the omega, if you decrease it, the oscillations will be slower, and if you increase it, it will be faster, because it's like how many oscillations per second. In a very naive sense, it's not exactly how many oscillations, it's in radians, but you get the point. You increase it, you will get more oscillations. You decrease it, you will get less oscillations. And then if you say there's a, instead of 0.02, then if you put 0.01, then the height of oscillation will be very less, like it will be 0.01 meters. If you put 0.05, then it means scale of motion, it will go up to 0.05 meters in the oscillation. So we will visualize these eventually. So that's it about the point displacement, and you can choose the values, you can play with the values and see what suits for your case setup. So as of now, I'm just going to close these. So now let's go to the next folder, which is the constant folder. Here we have 4 files. So this is the gravity file. As you can see, we have the gravity in negative 9.81 meters per second square. So that's how the geometry is made. So I have kept it this way. You can choose on which direction do you want the gravity. Coming to turbulence properties, as I said, we are going to use Spallet-Almaraz turbulence model, which is part of RANS. So we just declare it this way. And this needs nu t and nu tilde. That's it. Okay, and coming to transport properties, we are basically using air and it's a Newtonian fluid. So I have mentioned Newtonian. So coming to the most important file under constant, we are in dynamic mesh dict. So this is the file that is going to call your points displacement and say that this mesh is going to be dynamic and the mesh has to morph. So here we are having set of commands. You can see that we are first saying that this is a dynamic finite volume mesh, and the solver which we are choosing is dynamic motion solver FV mesh. And under motion solvers library, we have lib fv motion solvers.so. So these two are like mandatory and you can't change it. Coming to motion solver, we have chosen displacement Laplacian, but there are other options as well, like velocity Laplacian and so on. So when we choose displacement Laplacian, we are able to do mesh morphing, which is required for this case. So if you are trying to imply a very similar physics, then you can choose this one, or you can look at other options as well. You can find other options in the documentary. So when we choose displacement Laplacian, we have to give displacement Laplacian coefficients, which is like a dependent variable for this one. So this requires you to give diffusivity, and for diffusivity we are choosing inverse distance function and passing in cylinder. So cylinder is the patch that is going to move, so the naming convention has to be exactly same as what we are doing in here. So you can see that we are defining it in cylinder. So this is the word that we have to put here. So this has to be consistent. Okay, so after we do the dynamic mesh dict as well, we can save it, and then we can go to the systems folder. So under systems, I don't have a lot to explain. We are just using PimpleFoam, which is a transient incompressible solver, and we are using adaptive time stepping. So you can see adjust time step as yes, runtime modifiable also S, so that you can change the end time even when the simulation is running. I have chosen the initial delta T as 2e minus 4 and right interval as 0.01 seconds with adjustable, which means for every 0.01 seconds of simulation time, we will get result outputs. So that's what it's saying here. Right format is ASCII with a precision of 7 decimals. So nothing much to explain here, and FE schemes and FE solutions are very regular. I have used the airfoil 2D tutorial to take the FE schemes and FE solution. This works just fine for me, so I'm just going to keep it this way. And coming to decompose par, if you want to run it in parallel, then you can put the number of processors, the physical processors you have in your desktop or laptop, and you can keep the method as scotch. It will work fine. So for dynamic, for parallel computing, you can open your task manager, go to performance, CPU, and see how many number of cores you have, and you can use that value here. If it is AMD PC, if it is an Intel PC, then you can see how many number of physical cores you actually have, and you can enter that value here. So that's all about case setup. Now it's time for doing the actual case and running the simulation. So I'm going to right click here and open a terminal. Okay, and I'm loading my WSL. Now my WSL is loaded. In my PC, I have two versions of OpenFOAM, version 12 and version 2406. So I have to specifically load version 2406 because that's what we are going to use in this tutorial. If you don't have two versions, you can skip this part. Okay, now we are jumping into tutorials, and this is common for all. If you decide to use the mesh which I give you, like which comes with this case, then all you have to do is import the fluent mesh, which is like fluent mesh to foam, and then followed by the file name. So you just have to type this and the file name, which is in .msh, press enter, and we will be getting the mesh. So to view the mesh, we will create a Parview file, and I'm going to open this in Parview. So this is the mesh which we have. Since it's 2D, let me go to 2D mode. Okay, and looking at the mesh, you can see this has slight boundary layers, and the mesh is decent. Like it's not very fine, not very coarse, it's medium mesh. So this is the mesh which we are going to use, and you can see the left is inlet, and we have an outlet at the right, and upper and lower, and then we have the cylinder, and this is like front and back planes, but z direction is just one cell, so it will be considered as 2D. So these are just things which we generally discuss in our videos. Now going back to the actual simulation. So if you want to start the simulation, then all you have to do is first check you are in the right directory. You should be able to see 0, constant and system. Then first copy your 0.original and put it in 0 so that you have the 0 folder. Then all you have to do is type PimpleFoam and the simulation will start. So this is if you want to run it in series, but let's say you want to run it in parallel to make things faster. Then first you have to do decompose par, and then you have to do npi run np. In my case it's 8, it's the number of processors, and it's PimpleFoam hyphen parallel. So if you type this, the simulation will start, and for every 0.01 seconds of simulation time you will be getting one result output that you can just visualize here. Actually, first you have to go to decomposed case, then click apply, and you can see it here. Instead of surface with edges, I'll go to surface, and maybe put velocity. Okay, you can see that the cylinder starts to oscillate. If I go to surface with edges, sorry, go to solid color, you can see the mesh moving in here actually. I'll refresh once more to load more files. I'll go to the first time step and okay, I hope you can see the cylinder moving up and down slowly. So if I zoom it out, you can see that rest of the mesh is not changing much. It's just accommodating the motion with slight morphing here and there. Right? So this rendered video is something which you saw at the intro of this video. So that's exactly what you'll be getting if you follow the same boundary file setup for the entire case. After we load more time steps, if you go to surface back and if you choose your cell displacement, you can see how much of displacement is happening in each location. I'll go to latest time step so you can see that. Okay, so you can see it's very uniform on how it is changing. And if you go to other parameters like pressure, velocity, you will be able to see the data. And maybe if I go to velocity, sorry, yeah, so you can see that there are vortex sheddings happening and the cylinder is also moving. Because of that, we are getting some more um, oscillations in the flow. So this is what we are aiming in a vibrating cylinder, like what you saw in the intro video. Before looking at how to save the animations, we have a small announcement. If you are someone who is just starting with OpenFOAM and you are looking for a course, then we have got just the thing for you. So we have a Udemy course on OpenFOAM for absolute beginners. So we will give a coupon code in the description. So this will give you the best price that is available on Udemy as a discount. While making of this video, this has the best price of rupees 499, which is 82% discount for India, and you can open the link and see what is the discount for rest of the places. So this course is rated a premium course, which means top 3% of business level courses, and it has a rating of 4.6 with 96% ratings. We have almost 550 students enrolled in this course as of now. But if you're someone who is not interested in taking up a course, doing the quiz, doing assignments, and you just want to know the content and learn, then we have uploaded the exact same videos which is there in the Udemy, but this is a members only playlist. So we will give the link of this playlist in the description. You can check it out. The first video, which is this, has a detailed explanation on whether you have to choose Udemy course or YouTube course, which will suit you, what are the advantages, disadvantages, and everything. So if you are interested in taking up the course, then maybe watch the video so you can find out whether Udemy suits your method of learning or is it YouTube. If you think this course will be useful to any of your peers or friends, kindly consider sharing it to them. You can also share the link of the channel where we have been posting a lot of free OpenFOAM videos for beginners as well as intermediate level. So if you have not subscribed to the channel, consider subscribing it to it. So we will be motivated to make more useful videos on OpenFOAM and other technical topics. So back to the video. So once you click on the refresh, you'll be able to see more and more time steps. So let's assume that all the time steps have been done and the simulation is over. So what we have to do is, like, you can set any of the simulation parameter that you want, whether you want to observe the velocity or do you want to observe the pressure. Then you can align whatever you want, and you can also change the color maps by pressing this button. So you can change and assign whatever you want, and then what you have to do is click on file and click save animation. We give it a name, so I'm just going to put as trial 1 and then click on OK. Now if you want a decent resolution, you can keep it just like this, but if you want higher resolution, you can press this and go to 2x. And for frame rate, what I generally do is, like, I go to the control dict, okay, and I just take 1 divided by my right interval. So this will be like a simulation time to physical time, it will be coinciding. So if it is 1 simulation second, then it is also 1 physical time second. So you can see the animation in real time. So that's what I generally do. So in this case, if I do 1 divided by 0.01, it's going to be 100. So I'll put 100 frames here, and then if you click OK, the animation will start saving, and in whatever location you have given, it will get saved there. So for now, I'm just going to give it abort. I'm not going to let it save. So if you go to that location, you'll be able to see that that MP4 file is saved. And if you open, you should be able to see the animation. Yeah, so it's working. So this is how you save the animation. I hope this video was useful. If you enjoyed the video so far, consider dropping a like, maybe consider subscribing the channel for more useful videos. If you have any suggestion for CFD related videos, kindly drop it down in the comment section, or you can reach out to me on mail ID at codedynamics@gmail.com, or through LinkedIn. We have the company page Codedynamics where you can DM us. Thank you for watching the video till the end. See you in another video.